Oh, if I have any WebAssign problems we need to work? Yeah. All right, good deal. Get us some scratch paper here. You got it pulled up, or you waiting on it? Yeah. Okay. All right. Let me just pull that one up then. The number 5. Is that what it was? Once you get going on it, it's not that bad. It's maybe a little confusing to figure out what it wants. So, this was one of the more tedious ones. Sorry, this assignment is just a lot of the problems are kind of tedious. In this section, when we're doing the numerical estimates of limits, they get kind of rough a little sometimes. So this one's giving us one of the points on the curve. It's giving us p's 5, -3. Then it tells us the other point q we want to use. We use the numbers it's given us for the x value each time, and then our y value we plug into the function, so it'll be 3/4 minus the x value. So I think we do one of these. So let's get it set up. And then we're looking for the slope of the secant line there. So one of the points is 5, -3 on mine. Your number is probably different. Yeah, it's point P. And then Q is going to be x, comma, what was our function? 3/4 minus x. So we'll use both of those on each one of these little steps. The thing that changes on each one is x. And then we find the slope. So I guess I'll go down to the second one. Looks like we did the first one. I'm on Roman numeral 2 there. It says we want to use 4.99 for x. So equals 4.99. So then our slope, and they're calling it, well, I'll label it like they do. They're calling it the slope of the secant line through P and Q. Will be our slopes y2 minus y1. And so you can switch the order on these. I'm going to use P as my point 2. So I have -3, the y coordinate of P, minus, then we need the y coordinate of point Q. That thing's a little messy there, right? That's 3/4 minus 4.99. And on the bottom, we subtract our x value, so 5 minus x, which is 4 point. And then we just have to figure out what number we get. And how many decimal places does it say? It says 6 decimal places. So the part in the brackets there, the 3 over 4 minus 4.99. Figure that out. So you don't have to write this part down when you're doing them, but to give you some clarity here, that bracket part, 3.030303. We round a little. You don't want to round too much. You want to leave a bunch of decimal places because we've got to give our answer out to 6 places. So 7 might be better to keep right there if you're writing it down. You can just keep the number in the calculator. Anybody else need a sign-in sheet? I'll just put it up here on the front table. You can get it on the way out if you need. And then 5 minus 4.99. That on the bottom. We figure all that out now. So -3 minus a negative, so it turns into plus 3.030303. I'm going to go ahead and add an extra 0.3 in because I know that's what it was, just to make it a little more accurate. And divided by 0.01. Yeah, for the slope. That would be that one. To help any see what numbers go where. And then once you've got this set up, the next one's not as much work. I mean, you got the calculator work, but the next one now we're doing is we're switching the 4.99 out for 4.999, I think. Once you get all that set up, it's just calculator work most. Plugging into the slope. Help enough? Do we need to do another one or step on it? I have a different one we need to look at. On 6. Okay. 6. What's going on 6? Balls thrown in the air. The velocity mine says of 46 feet per second. T seconds later, given by y equals 46t minus 16 squared. Find the average velocity for the time period beginning when t equals 2 and lasting each of the following. So this one, same idea, we want the slope between 2 points. And this one gives us y equals 46t minus 16t squared. My numbers, just already forgot, 16. And then on the first step, it tells us we're starting at t equals 2. And on Roman numeral number 1 there, it says we want to go at an interval of 0.5 seconds. So our points we're going to use, one of them is going to be 2. If we go out half a second from that, that'll be 2.5. If you want to label it like we did the last one, call those P and Q. Then we need to figure out what the y values will be. So for that, we're just plugging into t, whatever equation it gives us. So 46 times 2 minus 16 times 2 squared times 4. Y coordinate on that point will be 20. So then now to figure out the y-coordinate on Q, I'm going to plug in 2.5 for 46 times 2.5 minus 16 times 2.5 squared, 15. I forgot my parentheses. Then we want the slope, or average velocity, or we saw that was the same thing as the slope of the tangent line, the secant line through those 2 points. So let's see, y2 minus y1, 2, so 13 over 0.5, 26. And that's feet per second. At this point, you don't have to do again because it's always on each one, it's going to be 228. So it gives you the x coordinate, so you just have to figure out the y coordinate at the next point. These are a little, like I said, they're tedious because you're doing the same thing several times. And then you look at the pattern 1 through 4 to see what it's going to be. Other ones giving anybody any trouble? Does that give you 7? Really simple. Anytime we need to talk about homework problems, we can. Don't be shy about bringing any up during class time. It's a good use of our class time. If you're struggling with a particular problem, you're almost guaranteed not to be the only one that's struggling with that one. Yep, several people, if not everybody. Get on the right notebook. Okay. So, moving our next section on chapter 2 still. This section is short lecture-wise. So what we're going to do, we're going to see some algebraic properties that limits have, and a couple of techniques we can use to find limits. And then we'll just do several examples. So the lecture's short. We've got just 15 slides. And then we'll work some. And again, I won't keep it the whole time because it's Friday. Try to let you out a little early. So in the last section, we got the idea intuitively. Here you could say we talked about what it looks like on the graph to find a limit. You follow the graph down its y values as x values are getting close to a certain number and see what value we're approaching. And then we did the same thing with tables of values where we plugged in numbers that were closer and closer to some value, and then we saw what we were getting at as our y value pattern or our f of x value pattern. So in this section, we're going to see these things we're calling limit laws. They're just properties so that once we find the limit of one little piece, we can, so like one little function, like we want the limit of the function, just x, something like that, then we can build up and figure out limits of more complicated things analytically, where we don't have to see the graph, we don't have to make a table of values. That's where we are headed to. Our 5 limit laws. I'm not going to make you write down the definitions or anything. You just need to know how to use these things and when you can use them. You'll be in good shape. So number 1 says if we want the limit two functions that are added together. Okay, so we're trying to take the limit of a sum. We're adding two things together. Then the way we can do that is we break it down into two pieces. It works out so that the limit of a sum is the same thing as finding the limit of each piece and adding those limits together. So we can find the limit of each simple piece and add those together, and we get the limit of the complicated thing. Same thing's true with subtraction. So in words, you could say the limit of a difference, the difference of the limits. If you want to, you can think about we're switching the order that we're doing the operation. Like number 1, we would start inside and have to do the addition and then find the limit, but we could also find the limit of each piece in it. So for plus or minus, easy to work with. Number 3 says the limit of c times f of x, c times the limit of f of x. So c here is just some constant number. So as long as we have a constant, not a variable, but if we have a constant, then to figure out the limit of that constant times some function, we can just find the limit of the function and then multiply it by that constant. Or another way you could say number 3 is if you have a constant factor inside of a limit, you can factor it out in front. Or can be really helpful. It says if we have want to know the limit of a product of the limits, find the limit of each piece, and then follow those answers. And number 5 says if we want the limit of a quotient, fraction, that's the limit of the top over the limit of the bottom. But division always gives us a little more trouble because what can we not divide by? Can't divide by 0. Right? We get an undefined situation then. So since the bottom here is the limit of g of x as we approach some value, then we can't do this if the limit of g of x is 0. So we say the limit of g. And that's a little more likely than you might be thinking because it's possible for the value g of x to be different than the limit of g of x. Saw that earlier. So just because g of x is not 0, we still have to think about what the limit of g of x. We really don't care if g of x is 0 or not. We just want the limit to know. Little subtlety to that. And the next couple of slides are just saying these in words. Well, if you want to see them in just plain English instead of in the math nerd notation. So the limit of a sum is the sum of the limits. Means we can break it into pieces. Limit of a difference is a difference. Limit of a constant times a function is constant times the limit of the function. Same thing with product. Limit of a product is product of the limits. It's boring to talk about, but it's really nice to use these properties. And then number 5, got the limit of a quotient is a quotient of the limits as long as the limit of the denominator is not 0. A constant would be like we're talking about like 3 times something. The 3 would be a constant, right? As opposed to a variable x, right? So something with a fixed value. So if you've got 3 times f of x, you just find the limit of f of x and multiply it by 3. Or I mean, it can be other numbers too, right? It can be pi. Pi is a constant. We'll see some. Okay. Other questions on what any of those mean? All right. So let's look at this one. This example is kind of neat because we're using these limit laws, but we're also using a graph. So look at this. I'm going to evaluate the following limits if they exist, so we're not guaranteed. So part A might be a little small, but we want the limit as x approaches 2. So here's our x value line we're approaching of f of x plus 5 times g of x. So if we want to use our properties, we could break this thing down. We could, you don't have to do this every time, but to say that, oh, it's -2. Sorry, I didn't see the negative myself. We're actually over here. It says x approaches -2, the limit of f of x plus 5 times limit as x approaches -2. What our properties let us do. We can split apart the addition. And then on this one, we use that constant factor. I did bring the 5 out front. So even though that thing's getting a little bit complicated, the only thing we have to figure out to be able to answer this is we need to know the limit as x approaches -2 of f of x. We need to know the limit as x approaches -2 of g of x. Let's look at our graph. F is the pinkish, purplish, magenta type color graph there. Okay. So as we're approaching -2, both sides, on F, what's our y value getting close to? 1. So that part's 1. At the limit as x approaches -2 of f of x. And that's plus 5 times the limit of g of x. Use the blue one, so as we get close to x value of -2, what's our g value getting close to? -1. So that's 1 minus 5, so the limit of that big thing we started out with is sort of. Look at B, it's even a little bit simpler because we only have one operation going on. So B, we've got the limit as x approaches 1, f of x times g of x. So our properties say we can break that down into the limit as x approaches 1 of f of x times the limit is x approaches 1 g of x. So x value of 1, that's this line. So on f of x, coming in here, so our y value is getting close to 2. G of x, coming in from the left, we're coming in down here. From the right, we're coming in up here. So what's our limit of g of x? Does not exist. Okay, remember if they don't match. So if the limit from the left side, the limit from the right side don't match, they don't exist. Not exist. So this whole thing, the limit of the whole thing does not exist. If we had gotten a number, we would just multiply the two numbers together. Okay. One more. I'll let distraction out of the way. So for C, if we use our limit laws, looking at the limit as x approaches 2 of f of x divided by the limit as x approaches 2 g of x. We're approaching positive 2, so that's this x value. Okay. So, let's see what's going on. We'll see here. So what I'm seeing is as we approach 2, we're coming in here, and I'm not sure what that value is going to be. Oh, it doesn't matter. I say 1, it doesn't matter. Yeah, so 1 1/3, 1 1/2, somewhere in there. So the top of this thing's like approximately 1 1/3 or something, but we really don't care because the bottom we have an issue. What's the issue there? Yeah, it's approaching 0, so we don't know what the limit is. On this one, okay, I said we have a little subtlety with division. Since we get 0 on the bottom, that doesn't mean the limit of this thing doesn't exist. It just means that we don't have a way of finding it right now. Because we get this 0 in the denominator, or our limit in the denominator, our properties break down, and our properties are not valid here. Find it. I think if you think about it. So if you have one like that in WebAssign, your answer is going to be D and E, but giving you the truth behind it. It's not necessarily that it doesn't exist in reality. It's just that we don't know how to find it. It may not exist. Questions on those using the graph? The limit laws? And I'm sorry. Yeah. So in WebAssign, what we would say slightly more precise answer is we're unable to find it. May not exist. Let me see what the textbook says on this one. So the textbook on this one is an answer of does not exist. Okay. I caught it around 1.4. That's too long then. We using the 5 exponent laws we have, we can extend these ideas and get some more limit laws that we. Number 6 is an extension of the product law where you have the limit of f times g, the limit of f times the limit of g. If instead of using 2 different functions, if we just use the same function over and over, f times f times f times f some certain number of times, then we get a power law. Number 6 says the limit of f of x to the n power. And that notation, the way they have that written, you may think about it a little easier if you think about it written like this. So what they're doing there, that notation, Oh, no, sorry, I'm thinking about the other side. What they're doing there, sorry, I just thinking backward there. What they're doing is they're doing the limit. Oh man. Oh, work with me. Of back to the limit, the left side. Now on the right side, the raising the limit to that. So any exponent we have, we can just find the limit of the thing we're exponentiating, and raise the limit to the English version of. And then we got two special cases that are the simplest limits we can have. Need to keep these in mind. Okay, they're easy, but if you don't think about it much, sometimes they'll trip you up. 7 says the limit of any constant is just the constant. So the limit as x approaches a of c is c. And the thing that can make that one confusing is the x approaches a part in here where x is approaching some number. Okay, if the thing we're taking the limit of is a constant, we don't even care what we're approaching. We don't even have to look at that part. If we're taking the limit of a constant, it's just going to be that constant. And you can think about that graphically, right? If we have y equals c, right? We got some constant function, then that's a horizontal line. So we don't care what x value we're at, our y value is going to be whatever that constant whole plane, at least over the whole domain. Limit of a constant is constant. And 8 says the limit as x approaches a of x, just our basic x to the first power there, is going to be a. And again, you can think about that graphically, because here we're thinking about the line y equals x. That's our function. Right? If you could say f of x equals x or y equals x. So here, if our x values are approaching a, so this is getting close to a, it says our y values also have to be getting close to a because they're equal. Thinking about that graphically, what does the graph of y equals x look like? Just a 45-degree line, right? And the thing that's special about it is, what do the points on the graph look like? The x coordinate and the y coordinates are the same, right? Because y equals x. So the point 1, 1's on there, point 2, 2's on there. Any point where the x and y coordinates are the same, that's y equals x. So if our x value is approaching some number, that means our y value has to be approaching that. So those are our building blocks. Got the 5 limit laws we saw to start with. We can extend the product to the power law. And we got these 7 and 8's kind of our basic building blocks. And now we can do a lot. We can actually figure out a lot of different limits by putting these things together. And so anything where we add, subtract, multiply, divide, or raise to a power, we can do any combination of that stuff and figure out the limit. That's a lot going on. And then we can even extend a little bit more. Because if we think about our power law, so we've got the limit as x approaches a of x is a. if we apply the power law there, we get number 9 here, which is really nice, really helpful. It says the limit x approaches a of x to the n. How do we find that? We just take whatever number we're approaching, that's the limit of x, and raise that to the n power. Really useful. And also do something similar with roots, radicals. Same idea, just instead of x to the n, nth root of x, how could we rewrite that in exponential form? Remember? We've got the nth root of x. That's the same thing as x to what power? 1 over n. So really we're just using 9 again in that form. So that says if we want the nth root, the limit of the nth root is just nth root of whatever number we're approaching. One more. In that, say if we want to take the limit of the nth root of a function, the nth root of the limit, root law there. But we do have a little caveat on that one. We're assuming we have an even index, because what if our limit turns out to be a, when we have positive here? Because we've got the issue with negatives under radicals. Sorry, I know it's kind of boring going over the laws. We'll get to doing some examples. But okay, here's the payoff after having to sit through all this. Payoff. We get this property that is really nice. It makes this whole finding the limit process much easier than it could be. That's this property. You take all of our limit laws that we've looked at, put them together, we get this property. This says if f is a polynomial, okay, so this applies to any polynomial. Polynomials are just when we have coefficients with different powers of x added or subtracted together, which is a lot of functions. Or we have a rational function. What's a rational function? That's when we have one polynomial over another polynomial. And then a is in the domain of our function. Then all we have to do to figure out the limit of our function as x approaches a is find f of a. So this is saying to find the, so let's take a polynomial for instance. To find the limit as x approaches a of some polynomial, we just evaluate the polynomial at a. We just plug in a for x. That's all we have to do, and that's the limit. And that works with polynomials and rational functions. For every value in the domain with rational functions, it's possible that you have some number that's not in the domain. Nice. And this is the result of something we're going to look at in the next section, that polynomials and rational functions have this property we call continuous or continuity. We will look at that little property more in depth, but right now we just want to. So let's do that. Let's look at some examples, then we'll come back and finish these. We don't have many. Guess I don't want that. Anybody have big, exciting weekend plans? Nothing you can talk about? I got secret weekend plans? Let's see, we want to find the limit. This one as x approaches 3 of this polynomial. So hang in there with me on this first one. I'm going to do it two ways. I'm going to do it using strictly the limit laws, and then we'll do it using the direct substitution property, just because I want you to appreciate how nice the direct substitution property is, how much work it saves. So first, let's do it just using our limit laws. So we got to break it down into pieces using the limit laws. So get tired of writing the limit notation on these for sure. So we've got 2x to the third minus 4x squared plus x minus 2. So I know I can break each one of those up using the addition and subtraction properties. This would be the limit 2x to the third minus the limit of 4x squared plus the limit x approaches 3 of x minus the limit x approaches 3 of 2. Then for on the first two terms, we're done. Okay, we're ready to find the limit on the last two terms because we know the limit of x, right? That's one of our building blocks. We know the limit of a constant. That's one of our building blocks. The first two we would still have to work with some more. One thing we could do is we could bring a constant out front. And we can bring the constant out front of the next one. Bring everything else along. And then we'd have to go one more. Go one more because we could use our power law. And I'll be lazy about writing this one, but we could say we want the limit of x cubed, that's cube for the limit of x. The limit of x squared, that's the square of the. So now what we've done, we've broken all these down into our basic building blocks. We've got x, 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 and a constant. Those are the two that we can use as our building blocks. So the limit of x as x approaches 3. What's that one have to be? I'm gonna go back. Yeah, we got, where's the deal? Up there, yeah. Yeah, so the limit of x as x approaches some number is the number we're approaching. So the limit of x as x approaches 3. So we'd have 2 times 3 to the third. Same thing on the next one, it's going to be 3 again. Same thing on the next one is 3 again. And then we've got the last one. This is the limit of a constant. So the limit of a constant is the constant. So the limit of 2 is going to be 2. 2. Now, all of this, roll. all of this part using the limit laws, but we could do it skipping all those lines and go straight to that bottom line using the direct substitution property, because what does it say? It says if we want the limit of a polynomial, all we do is we substitute the variable x, in this case, for the number we're approaching. So we would need 2 times 3 to the third minus 4 times 3 squared plus 3 minus 2. So we get to skip this mess. Now we can just figure out this last part. So 3 cubes 27, so that's 54 minus 36 plus 1. 54 minus 35. 19. Anybody else get 19? So that direct substitution property is saving us a lot of work. I know it's boring to sit through all the theorems and then get there, but a lot of work. So in any problem where you're trying to find the limit, if the thing you're trying to find the limit of is a polynomial, all you have to do to find the limit is you plug in the number we're approaching for x, or for the variable, whatever it is. Do that arithmetic. Oh, there's our limit, 19. Also, look at another one here. Because the direct substitution property gives us another situation where we can use it. It says we can use it for rational functions as well. So we've got a function of t to the fourth minus 2 over 2t squared plus 5. The only thing at all we have to be concerned about on this one is whether or not when we plug in 2 we get 0 in the denominator. So we could just check that real quick. If we don't get 0 in the denominator, we're good, because the direct substitution property says all we have to do, as long as 2 is in the domain of our function, so that means as long as we don't get 0 in the denominator, we just directly substitute in for our variable. So let's just try it, and we might as well go ahead and plug the whole thing in, because by the time we just check the bottom, we might as well just check the whole top. So this limit should be 2 to the fourth minus 2 over 2 times 2 squared, 3 times 2, 5. On the top, that's 14. 16 minus 2. On the bottom, let's see if I can do without having to break out a calculator. 2 times 4 is 8. Minus 6 is 2. Plus 5 is 7. 14 over 7, which is our limit. Fairly complicated function. And because we've got all those properties, turn that into that direct substitution property. On that one? All right, we'll come back and do some more examples, but let's finish our slides up here. Direct substitution. Sometimes we'll get in a situation where the easiest way for us to figure out the limit, the two-sided limit, is for us to think about the limit from the left and the limit from the right separately. And then remember, we had that theorem that said the two-sided limit, it only exists and gives us some value if and only if both of the one-sided limits are that same number. So if the one-sided limits match some number, then the two-sided limit is. So that's another useful tool we can employ here. And then two more properties, and then one other little theorem, and then we'll do some more examples. Okay. Okay. Yeah, bro. Yeah, bye. Okay, if you need anything, if you need later, leave a little bit earlier. Not one to stress over. All right, so two more. This one says if we've got two functions, f and g, if we know that f is always less than or equal to g when we're around the value where we're trying to find the limit, then the limit of f is going to be less than or equal to the limit. So saying if we've got a function, we know it's always either bigger or the same as some other function, then when we take the limits, the limit of the bigger one has to either be bigger or the same. We won't use that necessarily by itself here, but occasionally this last theorem will be really helpful. And it's called the squeeze theorem. So what it's doing is it's taking theorem number 2 up here, and it's applying it in both directions. So we're thinking we got a limit function smaller than some other function and a function bigger than some other function, using both sides. It says if we've got 3 functions, and if one is always bounded in the middle, so f's always smaller than or the same as g, h is always bigger than or the same as g, then one way we can find the limit of g is if whatever a we're looking at, the value we're approaching, if the limits of f and h, the two functions on the ends, are the same, then that only leaves us one choice for the limit of g, and that's that same number. So if you got a function bigger than a function, a function bigger than a function smaller than a function, and one in the middle, if the limit of the big one and the limit of the small one are the same, the one in the middle doesn't have anywhere to go except that same number. We won't have to use it a ton. So when we do need it, it's really nice. Here's a picture going on. So here, the pinkish purplish one is the one we want the limit of. H is the one that's always bigger or the same. F's the one that's always smaller or the same. So right here at our a value, the limit of h and the limit of f are the same. So that proves that the limit of g has to be. I mean, you can see where it gets the name squeeze theorem, right? If you have one function that's squeezed between two other functions, it doesn't have anywhere else to go. It's got to be that same spot. Let's look at some more examples. Like I said, I won't keep you the whole time, but let's do some more that'll help you on the assignment. One that can be a little bit tricky. Or my handwriting's bad today. I always hated it when I had a professor or somebody where you couldn't read their handwriting. Terrible. Anybody have any teachers like that? You can barely read what they write. And then you go back and ask them and say, what's that say right there? And they don't know either. That's bad too. X squared minus 7x plus 12. So you've got several on the assignment. You can just use the direct substitution problem and you don't run into any issues. This is one where we do have an issue, so we want to talk about how to handle that. So a lot of issues we ran into trying to use the direct substitution property we can solve with algebra. So you see what our problem is going to be on this one? Yeah, if we try to do direct substitution in that denominator, we get 3 minus 3, so we'll get 0 in the denominator, then we're stuck. So what could we do? Anybody have any ideas on some way we could rewrite this thing without the x minus 3 in the denominator? Okay, good thought. So overhead. Good thought dividing by x. Okay, it's down the same path. Okay. Have to be careful on these because just dividing by x is actually messy. What we would need to divide by is x minus 3. And if we can divide it top and bottom by x minus 3, then the bottom is just going to be 1. Get rid of that. So that's what we're doing. We're doing your idea. We're just doing it. It's going to look a little different because what we can do is we can try to factor the top. Hope we get some cancellation. Or effectively, we're dividing the top and bottom by x minus 3. So this thing, now there's some subtlety to this. Well, let's write it down and then we'll talk about it. Top how's that factor? We need factors of 12 that add together and give us negative 7, negative 4, and if we do positive 3, it'll give us negative 12, negative 3, yeah. Okay. Oh, I left 3 off here. And then what we were hoping for does happen here. X minus 3 on top, x minus 3 on the bottom. The only reason we can write this like this, well, let me do one more writing and then I'll go box. X minus. So we just have to be careful on knowing exactly what we're saying. Write this down. If we did not have these limits over here, we just had the function part, this would not be true. Not be true because the function x squared minus 7x plus 12 over x minus 3 is not the same as the function x plus 4. Close, but there's a difference because the first one's not defined at x equals 3. So the two functions are not exactly the same, so we couldn't put those equal signs in there. But since we're talking about limits, we're okay because we're saying the limit of this thing is the same as the limit of this thing, and that's true because when we're looking for a limit, we're not at 3, we're just approaching 3. So we don't care that this one's not defined exactly at 3 in order to say this because we're not at 3, we're just approaching 3. So, but now the good news, after we do all that, getting the limit part finally at the end is really easy. What do we do? Substitute. So it's 3 minus 4. And we'll look at this a little bit later, but graphically on the graph, the only difference between these two functions is that this one has a hole at x equals 3, and they overlap everywhere except for that, so they have the same. So if you run into a situation where if you try to do direct substitution where you get 0 in the denominator, then one thing you can try is you can try factoring to see if you get anything to cancel out. And if you do, if you can get rid of the 0 on the denominator problem, then you can use direct substitution. How we're on time. Let's do let's do this one more. There may be one or two that are still a little tricky. And we'll do a couple more examples to start on Monday. Okay, but this will get you through 90% of this assignment if you want to work on it. Yes. Cool. Got this one in here really just to review the algebra. X is approaching -4. We want the limit of x plus 4 over x cubed plus 64. That's a -4 there. And then those signs together. We try to direct substitution should be our first attempt, because it doesn't take long to try that. We try direct substitution on this one though. This is one that gives us a problem. We try to plug in -4. Okay, obviously we get 0 on the top. We really don't care about that. If we only got 0 on the top, that would just be 0. Non-zero on the bottom. Part that gives us the problem is if we do -4 cubed. -4 cubed is -64. -64. So we'll get 0 in the denominator. So one strategy we can try is we can try to factor. If anything will cancel out, what you got? Oh, you're on the right track. You're on the right track. Yeah, as far as factoring the bottom. Yeah, you're on the right track. What you're thinking of is like if you have the, well, maybe you're thinking of one of two things. You're either thinking like if you have the difference two squares, so that's a plus b times a minus b. What it's not. So side note over here. Trying to factor here. I wish it was. This is not x cubed plus 4 cubed, unfortunately. Well, I mean, sorry, not wrong. Not that is actually that. It's not this. It's not x plus 4 times x plus 4 times x. We do have a pattern we can use though. We do have a pattern we can use. So, this situation we would call the sum of two cubes. You may or may not even ring a bell depending on who you had for algebra, how the semester went. But we do have a pattern. So here's a pattern for the sum difference of two cubes. I'll give them both to you at the same time. Okay, you might want to take note of these so you'll have them for reference. So let me actually write it down correctly. B cubed. Got two of these. One's a sum, one's a difference. So they both kind of have the same little pattern. The only thing that's different between the two are the signs, the pluses and minuses. We're going to have two sets of parentheses, both of these. So we'll have A and we'll have B. And the second set of parentheses is the part that's a little harder to remember. So we're going to start with A squared. And then what we're doing is we're going to go down by 1 on the exponent. So in the middle we'll have A. And then for the third term, we won't have any A's. And then we're going to do the same thing with the B's, but going backwards. So on the end, we'll have B squared. And in the middle, we'll have B to the first. So you get something that looks like this. That part's the same on both. The only part that's different are the signs in there, and there's a way you can remember the signs. The way you can remember the signs is SOAP. So first sign's going to be the same as you started with. Second sign's going to be the opposite what you started with. And then the last one is always going to be positive. So first one, we started with plus, so we're going to have the same sign plus. Then we'll have the opposite sign minus. And then the last one's always positive. For the difference 2 cubes, we start with the same sign, so minus. The opposite sign, so plus. And then the last one's always positive. So let's, on this particular problem, we've got the sum of 2 top one. Let's finish it out real quick and I'll let you out of here. So we're trying to factor x cubed plus 64. Top's no big deal, it's just x plus 4. Maybe using our pattern on the bottom, we're going to have x plus 4 times x squared minus 4x, that's minus AB, plus b squared, so plus 4 squared plus 6. Using our pattern where a is x and b is 4. So then get the cancellation we want. Our limit. Now we can use direct substitution. So what's left on the top? If we cancel something out, that leaves us a 1. Leaves us a 1, yeah. Right, a lot of people forget and think it's 0. So then on the bottom we've got negative 4 squared minus 4 times negative 4 plus 16. So negative 4 squared is 16 plus 16 plus 16. So our limit is over 4. It doesn't take that long to do, just because we spent the time talking about the pattern. If you got the pattern to reference. Questions on that one or the pattern? All right, have a good weekend. We'll do a little bit more in this section on Monday and then move on to the next one. Yes, I'm sorry. Move it so you can get the pattern. Yeah. Very good. Yep. Got a problem?
Yeah.
Okay.
Okay. I'll be honest with you. Test on those two. Right.
Because you kind of went with a pattern. Yeah.
But 3.1, I did basically. My numbers are
3,
X.
-3, and then yeah.
So what I did was 2 minus 3, 1.
Huh?
Got negative 3 divided by that. Be negative.
Yep.
Whatever.
Yep. So that's going to be your point. Yeah, you got that part. Yep.
And then basically I just minus
that thing.
0.7. I'm just
okay. Yeah.
that divided by point.
Okay. Yeah.
Got that.
I need to go to the 7th. That's why I'm going to tell. That's like 3 questions right
Huh. Okay. That's goofy. So yeah, try adding one more.
25 minutes.
Yep.
Pulling my hair.
But yeah, that's crazy. All right. Thanks for letting me know that.
Thank you.
Right. Yes. Yeah. Okay. So if this is what we start with, then X is our A, and then B 4. Okay, that's it. And my brain wasn't working on this. This should be A cubed plus B cubed. Yeah. So that make sense. Yeah. It helps if the teacher writes the right thing down. Can I help you with? Okay. I'll look into it. I don't know of any way, but I will double check and see if I can find anything. He had it set up where we're doing. Oh, okay. Okay. I'll see if I can figure out how. Yeah. Yes, I understand. Yeah, I've had several people ask about that. So, okay.